Hi everybody, so in this video I'm going to show you how to solve homogeneous second order differential equations. So a homogeneous differential equation is a differential equation where all the terms in the equation can be expressed as the functions of a dependent variable and its derivatives, where y is the dependent variable and x is the independent variable. And to solve these types of equations, we need to use this equation here, where we have an exponential term multiplied by what's called the auxiliary equation. And it is understanding where this equation comes from that we're going to focus on in questions 1 and 2. In question 3, we'll look at applying this auxiliary equation to solve the differential equation. So in question 1, I'm going to show you that this exponential term is a solution to this general linear differential equation. And then if this is the case, then we can assume it will be a solution to a quadratic differential equation. Okay, so let's begin with question 1. So if you check out my previous videos in this playlist, you'll see that we solved equations of this form using an integrating factor. But before we do this, we need to make this coefficient of dy by dx equal to 1. So we'll divide both the left and the right hand side by a. So we get dy by dx plus b over a times y is equal to 0. And now we need to find an integrating factor, where we have e to the integral of p, and p in this case will be b over a, integrated with respect to x. And when we work out this integral, we get e to the power of bx over a. So it is this which is our integrating factor. And now we need to multiply the left and the right hand side by this term. So we get e to the bx over a times dy by dx plus e to the bx over a times b over a times y is equal to 0. And now can you see that the derivative of e to the bx over a is given here, and the derivative of y is dy by dx. So now we can use the reverse product rule, where d by dx of e to the bx over a multiplied by y is the simplified version of this left hand side, so this is equal to 0. We can integrate both sides with respect to x, and we get e to the bx over a times y is equal to the integral of 0 with respect to x. So we have the left hand side, and this is equal, and when we integrate 0 with respect to x, we just get a constant term, which we'll call capital A, and now we'll divide both sides by the exponential term. So we get y is equal to a times e to the minus bx over a. And you notice at the start of the question, we said that minus b over a is equal to m. So we can simplify this as y is equal to a times e to the power of mx. So what this means is, if this is a solution to a linear differential equation, we can assume it will also be a solution to a second order differential equation. So I hope that's given you an idea now of where this bit of our equation comes from. In question 2, we're going to focus on this auxiliary equation. Okay, so the auxiliary equation, am squared plus bm plus c equals 0, is formed by assuming a solution of the form a times e to the mx and substituting it into the differential equation. So what this means is, if y equals ae to the mx, we can use this to find dy by dx and then substitute that value into here. We can differentiate it again and substitute that value into d squared y over dx squared. So then we've got this equation in terms of e. So using the chain rule, dy by dx will equal am e to the mx and d squared y over dx squared will equal a m squared e to the mx. And now we'll substitute each of these into here. So we have a times a m squared e to the mx plus b, which is this term, am times e to the mx plus c. So a e to the power of mx. I'm just going to move this across a little bit, and all of this is equal to 0. So now we can simplify this left-hand side by factoring out the a e to the mx. So now we get the a term and the m squared term, so am squared, the b and the m term, so plus bm, and then we've already got this term here, so just c, and this is equal to 0. But we know that this term, this exponential term, can never equal 0. So the solutions to this equation must be from the quadratic. And when we solve this quadratic, we find the values of a, b, and c, which will give us these coefficients. Okay? So in question 3, we're going to use this auxiliary equation to solve the homogeneous second-order differential equations. So in the context of homogeneous differential equations with constant coefficients, the solutions can be classified into 3 complementary functions, dependent on the nature of the roots alpha and beta of the auxiliary equation, where capital A and capital B are arbitrary constants. You can see them here. So depending on these roots, alpha and beta, if they are distinct and real, then the complementary function will be in this form. If they are repeated real roots, it will be in this form. And if the solutions alpha and beta are complex conjugate roots in the form of a plus or minus bi, then the solution to a differential equation will be in this form. So in question 3, we're going to work out each of these 3 equations, and hopefully this will give you a clear idea on how to find the correct complementary function. So the auxiliary equation is am squared plus bm plus c equals 0. And you can see in question A that a is 1, b is 6, and c is 9. So we've got m squared plus 6m plus 9 equals 0. We can factor this, so we get m plus 3 squared equals 0. So this will give you our solution, our root, alpha, which will equal minus 3. So because it's only got one repeated real root, we're going to use this complementary function. So the solution will be a plus b times t multiplied by e to the power of alpha minus 3t. So this would be the general solution to this second order differential equation. In question B, we can see that a is 1, b is minus 1, and c is negative 12. So we can solve this. So we get m squared minus m minus 12 equals 0, which we can factorize to make m plus 3 and m minus 4. So alpha will equal minus 3 and beta will equal 4. And because we've got distinct real roots, we'll use this complementary function. So y will be equal to a e to the minus 3, this is alpha, plus b e to the 4t. So this will be the general solution to this differential equation. So finally, for question C, we know that a is 1, b is minus 2 and c is 5. So we get m squared minus 2m plus 5 equals 0. And when we solve this equation, we get complex roots of 1 plus or minus 2i. And in the form of a plus bi, we can see that a equals 1 and b equals 2. So now we'll substitute these two values of a and b into our complementary function. So y will be equal to e to the a, 1, times t, so e to the t, multiplied by a cos of b, 2t, plus b sine of 2t. Okay? And this will be the general solution to this differential equation. Okay, so I hope that's given you a clearer idea on how to solve homogeneous second order differential equations. If you found that useful, please hit the like and subscribe button, and you can download the full lesson from my website, mrmathematics.com. There's a link in the description below. Thanks again, and take care.